Challenger.
Welcome guys and gals. This is Rana, and in this video, we'll be looking at two claims from flat earth believers on why boats disappear bottoms up at distance. It is a 2-for-1 deal. Now, I did talk about one of these claims in details on my earlier video, Flat Earth claim boats over the curve. But I only had diagrams there. As I got my second-hand budget camera body, there is a video on budget photography for flat earth or globe earth in my channel. So with that, I guess I can have some actual photographs. Let's see the first claim. I will summarize what it is. Link would be in description, so you can confirm that I didn't take anything out of context. The video title is Angular Compression and Rayleigh Criterion Effect, the primary reason for bottom first disappearance. For those who may not be aware or may need a crash course, let me run through what they are, and you will immediately understand why this can never be the reason for bottom first disappearance. I'm standing across a small grassy area near my house. On the lamppost across me, I have stuck two electrical tape. These are standard electrical tape in UK. Starting focal, you can clearly see the two tapes and the gap in between. Now let's imagine a line coming from the bottom of this tape to the lens and another line from the top to the lens. The angle these two lines creates is called angular size. So whatever this value is, at this zoom level, that tape has a certain angular size value that is in degree. Now I will zoom out a little bit. As expected, the tape got a bit smaller. If you imagine those same line, now their angular size is less than what it was before. Similarly, if I had zoomed in, their angular size would be more than before. As I zoom back, at one point, we will not be able to distinguish those tapes anymore. And at the same time, I can see objects that are farther away. That is what part of Rayleigh Criterion is about. And this value, up to where we can see those tapes, is called angular resolution. The definition being the ability of any image-forming device, such as an optical or radio telescope, a microscope, a camera, or an eye, to distinguish small details of an object. In simple terms, when this angle is smaller than minimum angular resolution of the optics in question, it cannot be distinguished. Next thing to point out is, regardless what my focal length was, when we were able to see those tapes, we saw the whole tape. We know that because we can see the post above and below. The angular size has changed, the amount of pixels they occupy on the picture has changed, but at every shot, the top tape took up the same pixel height as the bottom tape. This is exactly what we expect. There is nothing blocking the view. This is what we should get on a flat earth. Either the object, depending on its dimension and distance from view, creates a resolution that we can resolve, or not. The moment it is resolved, we see both tapes completely. The only way one of those tapes would be partially visible if the view was blocked by something. When we look at ships, often we see them painted red on the bottom. We can make up any number to understand my point. Suppose after the load, visible red to rest of the hull is 1:10 ratio. Let's ignore refraction and curve just for a moment. Like our tape example, the moment the boat would be visible in pixel count, visible red and non-red portion of the hull would still have the same 1:10 ratio, and that is regardless the distance or focal length. The moment we introduce curvature of the earth, we have an obstruction blocking the view from bottoms up. As the ship moves farther and farther away, on our photograph, and it doesn't matter if it's my cheap second-hand F58 or a P1000, on our photo, the ratio will start changing. The red will get smaller at a higher margin than the top. And yes, as the red portion in our example is smaller than the remaining of the hull, its angular resolution would be smaller, and it would disappear first from our view than the hull. Hopefully this all illustrates how angular compression and Rayleigh Criterion effect has nothing to do with bottom first disappearance. Now you did notice that I didn't mention refraction, because as it happens, it is the next claim. This video cuts off abruptly, so I cannot be sure if I got the whole claim. But from the video title and the short clip, my understanding of the claim is, there is a 1986 master thesis document titled Propagation of Refraction Errors in Trigonometric Height, Traversing and Geodetic Leveling, which documents significant concave refraction during the day for gravel, grass and asphalt that also shows this refraction fluctuating throughout the day. I guess this is also a debunk video for someone named Clueless Miquest, who might have mentioned a standard refraction coefficient K value. And at the same time, it seems to imply that refraction is the cause of bottom-up disappearance, and he might be under the impression that we all use a standard K value. The thesis in question is 173 pages long. Full disclosure, I didn't read through the full 173 pages. Yes, I am lazy. And there is another reason. Reading from the abstract, the use of trigonometric height traversing as an alternative to geodetic leveling has recently been given considerable attention. A replacement for geodetic leveling is sought to reduce the cost and to reduce the uncertainty due to the refraction and other systematic errors. As in geodetic leveling, the atmospheric refraction can be the main source of error in the trigonometric method. This thesis investigates the propagation of refraction errors in trigonometric height traversing. I had to look up what geodetic meant in this context. Basically, it means leveling of a high order of accuracy, usually extended over large areas, to furnish accurate vertical control for surveying and mapping operations, often using a combination of a carefully designed and precisely constructed set of instruments like levels and rods. So as far as I understand from that abstract, some are suggesting usage of trigonometry to reduce the cost. Now, I don't think level and rods have refraction errors, but it can have human errors. Anyway, trigonometry method would suffer most from atmospheric refraction, and the thesis suggests 3 new models to calculate the refraction that has better precision of fit and are easier to utilize compared to the widely accepted Kukamaki's temperature model. Of course, I might be completely misreading it, but I read it as a replacement of an existing model to calculate the refraction we all know about. A standard value of K equal to 0.13 is often used in the survey. Another frequently used value assumes a light ray radius that corresponds to a coefficient of K equal to 0.143. Another frequently used value assumes a light ray radius that corresponds to a coefficient of K equal to 0.143. This is the reason, instead of using GitHub Earth Curvature Calculator that does not use refraction, we use Walter Bislin's Advanced Earth Curvature Calculator that uses the altitude to calculate this K value. So yeah, duh! And that's the reason there is no point of checking for peer reviews or even reading the thesis. But I will quickly touch on refraction. When a light moves from one medium to another, it bends on either direction based on the medium. There is nothing to dispute here. You should see a really neat photo of a polar bear in water. Note how the refraction causes its body to appear farther right than where it really is. Starting from the vacuum of space, when the sun ray enters our atmosphere, it bends. It continues to bend as it passes through all the gases in the atmosphere. But let's focus on water for a moment. Imagine a very hot day. You can even see the water evaporation from the lakes. Think of all those water molecules rising up. We have movement and water droplets. At least to me, it is fascinating to think the dance a light ray goes through to reach my eye. Whereas on a cold day, we don't have that same dance anymore. When we see this oil rig photo, we see a huge amount of shimmering. That is all the refraction that is going on there. The other prominent time this happens is when the sun is near the horizon. Out of all the wavelengths in light, blue is the shorter, smaller wave, and just the right size to bounce off our atmosphere. That is why most of the time the sky appears blue to us. But when the ray has to pass through more of the atmosphere, the blue gets scattered so much that by the time it gets to us, it's mostly red and yellow, causing the glorious sunrise and sunset. At the same time, due to this refraction, we see the light even though the sun is below the horizon, which means in reality, we see the sunrise couple of minutes before the sun is above the horizon and see the sunset couple of minutes after the sun is below. I do have a math video, refraction using simple math to flat earthers and why black swan images are possible, explaining how this happens. Link in description. So is there any other examples? I hear you ask. Oh, of course. During couple of months in the year, our beloved sun happens to hit the peaks of Mount Canigou in France, just enough to cause the silhouette to come into view from behind the curve. I have a detailed video explaining this, showing the sun path, and then there is seeing Corsica from Monaco during sunrise. Sometimes. You can also notice this when the sun is near the horizon, it appears flattened. Now, the ship and refraction. Yes, at times it is possible for a ship to be more visible due to refraction, but our earlier observation would still stand. Supposing the refraction brought more into view. When we're talking about the ratio of our imaginary boat, where the red to non-red hull portion was 1:10 ratio, as it is moving further at a calculated distance, ignoring refraction, it should be 1:20 ratio. But once it reaches the destination, we might find that ratio to be something in between. But in this claim, the argument is, refraction is causing the boat to lose visibility from bottom up. So if the picture is taken on a nice clear day and gentle sea, we would expect an average refraction overall, right? Which means, even if the refraction made the red part of our boat smaller, well, one, it would still be the whole view, just shifted. Remember our polar bear image? Unless, of course, it is obscured by something else. I don't know, like a curve. And two, wouldn't the refraction also affect the rest of the hull? Which meant, again in our photo, the ratio should remain more or less the same. A flat Earth does not allow that ratio to change, ever. Where globe Earth can predict the exact ratio if we can ignore atmospheric refraction, like where the object in focus isn't far enough to make any difference to our calculation. Or we can use a standard refraction and expect on average the result to match up with our prediction. I believe that explains why refraction cannot be an explanation of boat disappearing from bottom up either. Just to illustrate that atmospheric refraction can be different and even localized. You have seen the video earlier where we see enough refraction that caused a mirage. Well, here is some other larger aircraft taking off. And we can even see a post in view that looks straight and not shimmering. There is something called wake turbulence, and if you take a picture of an aircraft from behind as it is taking off, well, that would be a different kind of photo. Well, this is where I will end this video. thank you so much for watching. And I do hope you have enjoyed it, and maybe agreed as well. In either case, it would help me out a lot if you'd kindly subscribe. And if you have liked this video, I'm pretty sure you will like most of my other videos. Anyway, wherever you are, have a safe day. Signing off.
We are one people.